SAT of 1125 or greater. So what that means is I'm looking for the probability that someone's SAT score is greater than 1125. So what's my first step here?
Subtract the other 25 from the mean.
Find the z-score. You should always know when you're going to use z-scores because the question, I have to tell you in the question, assume the data is normally distributed. That is your hint to use z-scores. That's how we solve any normal distribution problem. So I convert this to z-scores. What is the z-score of 1125? It's 1125 minus the mean, which is 1,000, divided by the standard deviation, which is 100. So I get 125 over 100 is 1.25. So when we're converting to z-score, we're just changing the units. It's the same question. Now I'm looking at the probability that z is greater than 1.25. So this question and this question are the same, and we'll have the same answer. Do you guys remember from last week what we have to do when we have a greater than question? So the table we have is written all in less thans. But the complement of greater than is less than. So z greater than 1.25 equals 1 minus, this is complement rule, the probability that z is less than 1.25. And this we can actually answer using our table. So remember how we read the table. I have my first two digits are 1.2. So you have these two columns here. Here are all the negatives. Here are all the positives. I'm going to go to row 1.2, positive 1.2. And I have a whole bunch of columns then to choose from. My last digit is a 5. So I'm going to go to column at the top. You see the labels, 0.01, 0.02, 0.03, and so on. Well, I'm going to go to column 0.05 because this is a 5 here. So where row 1.2 and column 0.05 meet, I see 0.8944. You all see that? So my answer is 1 minus 0.8944, which is 0.1056. We do 1 minus because the original question is a greater than, but the table is not written in greater thans, so we have to use a workaround. And that workaround is the complement rule. Because the probability that z is greater than 1.25 plus z less than 1.25 is just 100%. Yes?
So anytime the z is greater than, we have to use the complement rule.
Correct. Every single time you have a greater than, you have to use the complement rule. Because what the table gives you is the less than. But 1 minus the less than is the greater than. Yes?
So if it's less than, then we just leave it as it is.
Exactly. If the question is a less than to begin with, then you just leave it whatever you get from the table. The table's already correct. If you want a percentage, this is 0.1056, and percentage, that'd be 10.56%.
Either one are fine.
Either one is fine. They're both the same thing. Let's look at number 2, or part B. What proportion of students scored between 950 and 1050? Probability that an SAT is between those two values. What's my first step? Always z-score. So I have 2 z-scores now. I need one for each data value. So I have 950 minus 1,000 divided by 100 gives me negative 50 over 100. That's negative 1/2. Similarly, 1050 minus 1,000 is 50. Divided by 100 gives me positive 1/2. So I've rewritten this as the probability that z is between negative 1/2 and positive 1/2. What's our procedure? So our table is not written in in-betweens, much like it's not written in greater thans. So what is our workaround for in-between probabilities? So this is where it makes most sense to draw it out here. here's negative 1/2, positive 1/2. And I'm looking for the area in between them. That's what the question's asking me for. If I look up positive 1/2 in my table though, it won't give me the area in between them. It'll give me all the area below positive 1/2, all the way to negative infinity. It actually never stops. If I look up negative 1/2 in my table, it'll give me, similarly, all the area to the left of that, all the way to negative infinity. If I take this chunk from here on down, and I subtract this piece, what am I left with? Just the in-between part, right? Does that make sense? So how do I take this and rewrite it in our notation here? That means I take the probability that z is less than my bigger z-score, the one further to the right. In this case, it's positive 1/2. Equals the probability that z is less than, and it has to be a less than because the table, I want the area to the left there. Positive 1/2 minus this piece here, which is the area below negative 1/2. So minus the probability that z is less than negative 1/2. So now, notice these are both less thans here. And that will always be the case with these in-betweens, because I'm considering the areas below those z-scores. So let's look up positive 1/2 on our table, which that's 0.50. So I'm going to go to row 0.5 and then stay on the first column or the 0 column. So positive 0.5. What do I get there? My final answer, I believe, is 0.3085. But just for this part, 0.50, what do you get?
0.6915.
0.6915. What about for negative 1/2? That's the 0.3085. So nearly 70% minus about 30%, about 40. Questions there? For this one here, for the positive one, the only difference between the left and right table is the right table's for positive z-scores, the left one is for negatives. It's all one table. It just continues up here because I ran out of page. It's all one table. Questions there? So if you have questions, don't be afraid to ask. We're going to use this table for this lecture and chapter 8, which is our last lecture. So we'll use this table for everything from now on.
So anytime you're trying to find in between, you have to break it up like you did there.
Yeah. Or use a computer, which you don't have on the test. So to use this table, this is how you do it. This is the standard way of doing it. Just the largest minus the smallest.
Yeah.
Do not, a common mistake I see is people subtract the z-score. So they'd have 1/2 minus negative 1/2 is 1, so the probability that z is less than 1. That's not at all what this question is asking. Subtract probabilities, not z-scores.
Yeah.
So in both of these questions, I gave you SAT scores, and then I asked some question about it. Yes.
Wait, if it was less than instead of greater than, would you still open it up like you did?
You mean here?
Yeah.
Anytime you're asked a between, it's going to look just like this. There's no other option. It's going to be the smaller number, the bigger number, and z has to be greater than the smaller and less than the largest if it's in between them. So it'll always be exactly like that. And in both of these, I gave you an SAT. You found a z-score, and then gave me a probability, whether it was greater than, as in the previous question, or in between in this one. We can also work in the other direction. I can give you a probability and ask you what is the SAT score. So it's just a reverse. We encountered something similar with the empirical rule. So what score would a student who scored at the 90th percentile have received? What does 90th percentile mean? She did greater than 90% of people taking the test. In other words, 90% of people did worse than her. And 10% of people did better than her. So let's say she's right here. 90% of people are here, 10% of people are here to the right of her. And the question is, what is this SAT right here? The score that cuts off this this 90th percentile. So, what's going to be my first step? It's to find the z-score. Still, my first step, find that z-score right there. And how do I find it? Well, I know that it's the z-score that has 90% of the distribution below it. So now I go to the interior of the table, and I'm going to look for 90%, or in decimal, 0.9. All these numbers are up to 4 decimal places. So what I'm looking for is 0.9000, or as close as I can get to it. I'm not going to find it exactly on this table, but we'll see how close we can get.
1.29.
It appears to be 1.28, 0.8997. So I heard someone say 1.29. That's fine, because what is that difference is that going to make in the final answer if I use 1.29 versus 1.28? Not much, right? We're talking about 1/100th of a z-score. So get as close as you can. If you're off by 0.01 or 0.02, you'll probably be fine. Because remember on my test, I put the answers spread out, and you're going to pick the closest one to what you calculated. But here, the closest we can get is 0.8997. That's on row 1.2, column 0.08. So that z-score is 1.28. Meaning that anyone that scores at the 90th percentile did 1.28 standard deviations above the mean. So I take the mean of 1,000 and add 1.28 standard deviations, which was 100. And it comes out to 1128. This here is the mean plus z times sigma, which if we look at our z-score formula equals x, our value. This is our z-score formula. If we solve for x, which is what we're doing here, you get this, mu plus z sigma. Questions there?
What part of the chart did you look at again?
To get the
1.9000?
I was looking for this on the chart. This does not exist on the chart. So I found the closest thing, which was 0.8997. That's only 0.0003 below this, so that's as close as we can get. And that was on row, this value was on row 1.2, column 0.08. That's where we got 1.28 from.
So the answer is 11.
This would be the answer here. This is the SAT score that is the dividing mark between the lower 90% and the upper 10%. Yes.
I have a question for the last one.
Uh-huh.
For the probability of z-scores less than 0.50,
Uh-huh.
so it's always in that range, highest to lowest, or the biggest to smallest.
You always put the large, this
Uh-huh.
positive a half is a greater number than negative a half, right?
Because you're subtracting and you want to get a positive number.
Right, it has to be. So, I mean, remember, I'm not subtracting the z-scores, I'm subtracting the probabilities. But yeah, I need to get a positive number.
So then you would subtract
0.6915, which is what I got when I looked this up, minus 0.3085, which is what I got when I looked that up.
because those are the area probabilities. Okay.
Yes, that's it, and then I'll give you the area between the two. All right, let's then look at the binomial distribution. So we learned 2 distributions last week. The normal distribution is a continuous distribution. The binomial is a discrete distribution. Discrete meaning that the binomial, I can only compute probabilities for integer values. Okay, so let me write up the binomial formula. Remember, this is not n divided by k, this is n choose k, times p to the k, times 1 minus p to the n minus k. You toss a coin 5 times. For this coin, we have probability of heads is 60%, and thus probability of tails is 40%. What is the probability of getting exactly 2 heads? So there's 3 variables in this formula. N is the number of trials. In this case, it's the number of times I flip the coin. So what's n here? 5. P is the probability of success at each of these trials.
0.6.
We define success as by the wording of the question. Here it says, what's the probability of getting exactly 2 heads? So therefore the probability of heads is my probability of success, which is 60%, 0.6. And lastly, K is what the question's asking me for. It says the probability of exactly 2 heads out of these 5 tosses.
2.
So it's 2. Notice I didn't at all mention in here, assume the distribution is unimodal and symmetric. I didn't say assume it's normally distributed. This is just a K out of N situation. That's when you're going to use the binomial distribution. K out of N situations. So let's plug those values in. N choose K becomes 5 choose 2. P to the K becomes 0.6 squared. 1 minus P, that's 1 minus 0.6 is 0.4. That's just the probability of tails. Why is that?
It's failure.
They gotta equal 1. Remember this part of it here, it's just multiplication rule. It's the probability of heads to the number of heads times the probability of tails to the number of tails. If I have n total tosses, k of them are heads, then n minus k of them are tails. It would be, it is, well, it's actually cubed to the power of n minus k. So n is 5, k is 2, because I have 2 heads, that means I have 3 tails. So that's why n minus k is 3. And this, of course, all gives me the probability that k equals 2. In other words, the probability that I get 2 heads out of these 5 tosses. And that's really the worst part of these binomials, is just making sure you've correctly identified these, which shouldn't be that bad. So I know the binomial formula looks very bad, but it's actually a very straightforward application when you use it.
I know over here the probability is given where it says p heads equals 0.6. Are you gonna do the same on the exam, or you're just gonna mix it up?
No, in the exam I have to give you P, right? You can't just make it up. I mean, I might say something like it's a fair coin, and then you'll know that it's 50%, 50-50. But yeah, all these have to be given somewhere in the problem. So once you have it set up, the first thing to do is find what this equals. 5 choose 2. That it's going to equal some number, and then you're going to plug that number back in.
Factorial.
So remember that n choose k equals n factorial over k factorial over n minus k factorial. So this equals 5 factorial, which is k factorial. I'm sorry, which is n factorial. On the bottom, I need a k factorial. K is 2, so I have 2 factorial. And lastly, I have 5 minus 2 is 3, n minus k. Notice the denominator values here in my choose function are just the same as my powers in the p and 1 minus p. Yes.
Will you get people?
I'm sorry?
Will you get the?
Because here I have an n minus k,
Oh.
5 minus 2 is 3. And it's the same as, for the same reason that I had an n minus k up here, is 3. So it's always going to be the same values, but with an exclamation mark. So that factorial, 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. Times 3 factorial, the denominator is 3 times 2 times 1. You're always going to get a lot of cancellation because the 2 numbers in the bottom have to add up to the number on the top. So they're always going to be smaller than this number. And when that happens, I get this 3 times 2 times 1 canceling with this 3 times 2 times 1. So I'm left with 5 times 4. That's 20. 2 times 1 is 2. 20 divided by 2 is 10. So now I know that this 5 choose 2 just equals 10. So I have 10 times 0.6 squared times 0.4 cubed. This I trust you know how to put in your calculator I actually don't have it figured out, so I'm not sure what it
Point
comes out
three
to.
zero four.
0.304.
0.2304.
0.2304?
Yeah.
So about a 23% chance that I'll get exactly 2 heads. Notice this is not 2 or more, it's not 2 or less, it's exactly 2 out of the 5 tosses. Question there?
Where did you get that four from?
This one?
No, from the force, yeah.
This one is 1 minus p. So we found that p was 0.6,
Oh,
so the 1 minus p is 1 minus 0.6 is 0.4.
Why is it, I understand why the 3, 2, 1 cancels out on that, on the
Mhm.
bottom denominator. What about the 2 times the 1, like, why does not?
So the thing, I can't cancel, I could have.
Like, do they have to, I mean, are you just looking for that same consecutive pattern and then you can
No,
cross
no,
that
no.
out on both
Any
sides?
number that's the same, except there's, now that I already canceled that 2, so there isn't 1 left here.
Okay.
So you're right, I could have canceled this 2 with that 2, and then I'd have that 2 left over, right?
But you would still have, okay.
But it's the same thing, it doesn't matter which. And now, I mean, depending on how comfortable you are, I can cancel that 2 with this 4 and call that 4 as 2. And then I'll just have 5 times 2 over 1, which is also 10.
So, Matt,
Yes.
so that's what the factorial, because last week I was completely lost on what the factorial did. So it's just kind of like breaking up the number.
The factorial function itself is, yeah, it's just the number multiplied by everything less than it all the way down to 1.
Okay.
And you stop at 1. What the choose function is doing is counting the number of sequences. Remember we had wrong, 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 right, wrong, wrong, right, wrong, wrong, right, wrong, wrong, and then right, wrong, wrong, wrong for the examples. And there was 4 sequences. Had I done 4 choose 3, I would come out with 4. It's just counting the number of sequences that exist.
Thank you.
Can you go over what N, P, and K stand for again?
N is the total number of trials. P is the probability of success at each trial. And K is the number of successes. So now you can think of K as just what is the question asking me? Out of these 5 trials where each one has 60% chance of success, I want the probability that I get exactly 2 successes. And that's what K is, the number of successes.
So where do you get 0.6? The probability of success.
At the very top, except for this coin, we have probability of heads equals 0.6. So part B here, what is the probability of getting exactly 3 tails? Without doing any work, can you tell me what that probability is? It's exactly the same. This was the probability that I get 2 heads out of 5 tosses. If I get 2 heads out of 5 tosses, then how many tails do I get?
3.
3. So there's always 2 ways to formulate these questions. Saying 2 heads out of 5 tosses is equivalent to 3 tails out of 5 tosses. So I could have asked this in terms of tails, said n equals 5, p equals 0.4, and k equals then 3. And you'll see if I plug it into this, I'm going to get the same thing. 1 minus p is going to be 0.6, n minus k is going to be 5 minus 3 is 2. So it changed where it is, but it's still 0.6 squared. P to the k would then be 0.4 cubed, which I already had here as well. The only difference is now instead of 5 choose 2, I would have 5 choose 3. Think of the definition of the choose function. Anytime that I have 2 different choose functions and these numbers on the bottom add up to the top, they're going to equal each other. So because 3 and 2 add up to 5, 5 choose 3 and 5 choose 2 equal each other. 5, most commonly we see this like in 6 choose 1 would then equal 6 choose 5. How does this make sense intuitively?
They're independent.
It has nothing to do with independence. Good thinking.
They add to the front,
I'm sorry?
they add the sum of those 2.
This, yeah, if this sum adds up to that, then they're equal each other. Because here, it's telling me the number of sequences where out of 6 objects, one of them is the same, let's call it the success, and I'm arranging that one success amongst these 6, the sequence of length 6. If I instead arrange the 5 failures in that same sequence of length 6, Don't I get the same thing? Much like saying in the sequence of length 5, how many different places can I put the 2 heads? That's what this function was counting, the number of places I can put the 2 heads. That gives me the number of sequences that exist. That's equivalent to saying where can I put the 3 tails. And that's why this is always true. Yes?
Can you just do the complementary of
It wouldn't be the complement because the complement would be 1 minus this. But the answer is actually, it's not the complement, it's the same. It would come out to 0.2304.
Why don't we, I mean, why would it not be like 77? You know, just minus the 23.
Right, because it's not the complement question, it's the same question. 2 heads, 3 tails out of 5 tosses, it's the same thing. If I get 2 heads, I must have had 3 tails. If I get 3 tails, I must have had 2 heads. So it's really just the same question being asked the other way. So this fact is not something I'm going to test you on, but occasionally it can make it easy to compute things. To try and make things easier, anytime you have anything choose 1, the answer is just the top thing. Therefore, anytime you have anything choose something that's just 1 less than itself, the answer is still just the top thing. Both of these just equal 6. 200 choose 1 equals 200. Yes.
So if we want to figure if it's a binomial question on the exam, would we just think of the fixed number of trials, all that, or would we look at keywords such as, I see exactly, I keep seeing exactly. The keyword
So exactly is, I mean, the word exactly is an English word. I could use it in, I can imagine some other context where I could use it. But that would be a hint to use the binomial. But what you're really looking for is anytime you have a k out of n situation. Something out of something. 2 heads out of 5 coin tosses. 9 buses are on time out of 10 buses. Just something out of something. That's the typical binomial application. So let's look at our next binomial example. At the bus stop near your house, there's an 80% chance the bus will be on time. Assume any given bus arrival is independent of any other. This just means the buses don't affect each other. Out of the next 10 buses, what is the probability that exactly 9 of them are on time?
So if it was asking for the probability of 1 being late, would be the same answer, right?
If it said, what was that question?
The probability of 1 of them being late would be the same answer.
Exactly. I could have just as well said, what's the probability that exactly 1 of them is not on time? Same exact question. So what is n here?
10.
I have 10 buses coming. Those are my 10 trials. What is the p, the probability of success here?
0.8.
80% chance the bus is on time, 0.8. And k, what the question's asking me. I want the probability that 9 out of 10 buses are on time. So I have 10 choose 9. Times p to the k would be 0.8 to the 9th. That's just multiplication rule, right? 0.8 times 0.8 times 0.8, 9 times for the 9 buses that are on time. So therefore we have 1 minus p, which is just the probability you're not on time, 0.2. These will always add up to 100%. And if I have 10 buses, 9 are on time, then how many are late?
1.
1, which is n minus k, 10 minus 9 is 1. So now let's do 10 choose 9. What does that equal? We just talked about it. 10. We know it equals 10 choose 1. Anything choose 1 is just n. So 10 choose 9 is 10 times 0.8 to the 9th times 0.2 to the 1st. And that gives me the probability that k equals 9. That 9 of my 10 buses are on time. So does anyone have a calculator and figured this out? The important part, of course, is setting it up right.
0.2684.
Thank you. 0.2684. Yes.
So whenever it's 10, choose 1, it's 10.
Yeah, 20 choose 1 is 20. 50 choose 1. Anything choose 1 is just itself.
Okay.
I don't know if you'll go over this today or some other time. I got really confused with the complement rule for the binomial. I don't know if you want to.
Complement rule for the binomial?
That it was an at least question or some. It was.
So I think the example I gave last week.
Yeah.
The purpose of that example was to show the value of the complement rule. I always said that if I ask you what's the probability of at least one heads given 5 tosses, well, the sample space would be 0, 1, 2, 3, 4, 5 for the number of heads I could get out of 5 tosses. At least one means one or more. So by addition rule, I would have the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 all the way through. That's a lot of binomials to compute if they're binomial probabilities. Much easier is to know that they all add up to 100%, subtract the probability of 0, and that gives me this. So I didn't add anything new to the complement rule. I just, now that we know binomial, I gave an example of why we really want to use the complement rule. Or we might end up doing 5 binomial probabilities, which would be very time consuming.
The powers, the 9 and the 1, do those have to equal the 10?
Yeah,
Why. So
'cause
anyway,
notice the powers
so
are k.
even if you change n, then those powers are going to equal whatever n is.
They have to.
They have to. Okay.
I mean, look, they're k and n minus k. If I do k plus n minus k, I get n, right?
Right.
That's always true, by definition.
Sorry, but is that negative 2.8?
It is not a negative, that's just a mark that was there. Remember, probabilities are always between 0 and 1, never negative, never above 1. Yes.
So going back to 2B, the exactly 3 channels.
Mhm.
I actually tried to do it using the formula and I'm getting a different response.
Okay.
And
It has to be
so-
calculated.
So it's 5 choose 3 is also equal to 10, right?
Yeah.
And then I got 0.6 to the third, or it's 0.6 cubed, and then 0.4
To the third.
to the third.
Well, if n is 5, then the
Oh.
powers have to add up to,
Point.
yeah.
Which is 0.6 would be squared times 0.4, because 2 plus 3 is equal 5.
See me during the break.
Yeah.
I think it's just, might be calculator.
I'm sorry, I don't know why'd you skip the choose multiple?
On this one?
Yeah.
So I didn't have to skip it. I skipped it because I had said that anything choose 1. Well, first I said that anything, if they add up, so 10 choose 9 equals 10 choose 1. Because choosing the 9 successes is equivalent to choosing 9. Choosing 9 successes is equivalent to choosing the 1 failure. So that's why these two equal each other. And anything that is anything choose 1 is just itself. So that's why 10 choose 9 and 10 choose 1 are the same. 5 choose 1 and 5 choose 4 are the same.
So n is the total, and then k is the trials, right?
N is the total number of trials, and k is the number of successes. So this sequence of length n is going to be full of only 2 possible values for each trial, success or failure. K is the number of successes, therefore n minus k is the number of failures. Questions there? So on this optional Saturday practice problem day, we will do more z-score and more binomial type problems. If there's no other questions, we'll start with chapter 7. So this chapter, chapter 7, I don't say this so that you go and forget all the other chapters, but I consider this chapter the point. If this class has a point, it is chapter 7. This is the reason we learn z-scores. So the first half of this chapter will just be introducing today's concept, which I consider the point of the class. And then the second part of today will be one application using that concept. And then chapter 8, all of chapter 8 is just an application of this idea. The idea being the sampling distribution. And we'll talk about what that means when we get there. So let me just give you the big picture here. If I take a poll and I ask what percent of you guys are like chocolate as your favorite ice cream, and let's say I get some number, 30%, and then I go to my Thursday class and I ask them the same question, am I going to get the same answer?
No.
No. Am I going to expect an answer close to the one you guys gave me?
No.
Maybe.
Why not? If you guys are a random, which you aren't, but maybe I could argue you're a random sample of SMC students. So I'm not going to get the same answer, but I'm going to expect to get a similar answer. We call that sampling variability. So let's say I know for a fact that of all people, exactly 40% like chocolate as their favorite ice cream, of all people. Then I take 30 of these people, that's my sample, and 35% tell me they like chocolate ice cream. I take another sample, this time I got 37. The next time I get 42. Because the true value in the entire population is 40, I always expect to get a number near that 40. But because these are random samples, that value actually changes a little bit from one sample to the other. Maybe I get 39, 41. That's called sampling variability. And I think I mentioned earlier in the class that statistics isn't about, it's about making estimates, but more specifically, it's about being able to quantify how wrong our estimates are. We know our estimates are wrong. The important question is how wrong. And that's what this sampling distribution will allow us to compute. So let's start with some terminology that you may have seen already. The population is the group of people or objects we wish to study, the entire group. A parameter is a numerical value that characterizes some aspect of the population. Like saying that 40% of all people love chocolate ice cream, that would be a parameter. A census is a survey in which every member of the population is measured. In this country, we do an actual census and we call it the census. We do that every 10 years, and our main goal there is to just count our nation's population. What's another example of a census that's common in this country? It happens every 4 years.
Election voting.
An election, voting. Every 4 years, we ask all eligible voters, who do you want to be president? That's an example of a census. They're very expensive, right, to conduct our census. That's why we only do it every 10 years. Elections are also very expensive. A sample would be a collection or a subset of people or objects from the population. So sample is just a small part of the population. A statistic is a number that estimates a population parameter, and it comes from the sample. So here's a population. I take some of those people. That's my sample. We're going to continue using n to mean my sample size. Remember, parameters relate to populations. They both start with p. Statistics come from samples. They both start with s. And we use statistics to estimate parameters. So if I want to know what the population mean mu is, well, I don't want to go take a census because they're too expensive. So instead I take a sample, I compute my statistic x bar. Remember, that's the sample average. And x bar is my estimate of mu. Similarly, the sample standard deviation, little s, is my estimate of sigma, the population standard deviation. Wouldn't it be better to just include everyone and sample the entire population, the census? Yes, that would give me the precise exact answer. But when CNN wants to predict who's going to win an election, do they hold their own election a week before our election? No, that'd be incredibly expensive and unnecessary. They instead take 1,000 people that they randomly call. They ask them, who are you voting for? And they get some percentage for some candidate. And they want to assure you that the percent they got is the percent that's going to happen in the actual election. And they use the same methods you're going to learn today to give you some margin of error, some how certain they are of their estimate. We call this inference when we use a statistic to estimate a parameter. Here's an analogy. If I taste a spoonful of soup and decide it doesn't taste salty enough, that's simply called exploratory analysis. I've looked at the data. If I then generalize that and conclude that the soup needs more salt, that's what we call the inference. For my inference to have been valid, what needed to be true? Well, I needed the spoonful that I tasted and made this inference based upon to actually taste like the entire pot of soup. If all the salt had settled at the bottom and I spoon from the top and I go, oh, it's not salty enough, and I add more salt, now my soup has too much salt once I actually stir it. So for my inference to be valid, I needed that original spoonful, the sample, to actually taste like the entire pot. We call that being representative. We want our sample to be representative of the population. So inferences are in science, depending on how you define these words, of drawing conclusions about a population on the basis of observing only a small subset of that population. Inference always involves uncertainty, and this is where statistics really comes in. An important component of this science is measuring that uncertainty. Opinion polls are examples of sample surveys. That's what we're going to talk about a bit here. Professional pollsters try to ensure that the sample is representative of the population, or their conclusions won't be valid. So let's look at a famous case here. Landon versus FDR. In 1936, Landon sought the Republican presidential nomination, opposing the re-election of FDR. The Literary Digest poll polled about 10 million Americans. That's a huge sample. They got responses from about 2.4 million. Again, a huge sample. It turns out that even if we get about 30, 50 people, even if our population is 300 million people the way the United States is, we're still going to get fairly accurate results. So 2.4 million, massive sample, we really expect accurate results. Their poll showed that Landon would be the overwhelming winner. FDR would get only 43% of the vote. In the actual election, FDR won with 62% of the vote. So what appears to have been the most likely issue here? The magazine was completely discredited and soon discontinued. This is why we've never heard of this magazine, because they were really bad at stats. What did they do wrong? Their sample was not representative of the population. They sampled their own readers, registered automobile owners, and registered telephone users. This was Great Depression era America. People that had magazine subscriptions, owned cars, and had their own telephone were not the average person in the United States. This group was not representative of the entire nation. This was a wealthier subset, and they had their own preferred candidate.
Just the more larger your like sample, the more accurate you can get.
Yes, assuming that sample is representative of the population, which here it was not. This was not representative of the typical American at the time. So what we want, and the way we accomplish getting a representative sample, is we want our sample to be completely random. This is not as easy to do as it may seem, and in fact, sampling techniques are an entire course in themselves. We're not going to get into sampling techniques specifically, other than to say the most basic is called SRS, simple random sampling, much like I can conclude causation in an experiment where I randomly split my test subjects. Now I can make accurate conclusions about my data if my sample was randomly chosen. So what this gets us to is the sampling distribution. The sampling distribution is what I started the class with. I said if I ask my Thursday class, what % of you like chocolate ice cream, I'm going to get a slightly different number than you guys. And if I ask another group of people, I'm going to get a slightly different number as well. although I expect them all to be close to whatever the true value is in the entire population. So let me illustrate this. Here, these circles just represent some sample. Let's say I have n equals 30 people. All these people came from some distribution. This is what we've seen so far in the empirical rule and the normal distribution with z-scores, even the binomial distribution. Now from this population distribution, we call this the population distribution, I choose a sample. And then from that sample, I ask them what percent of you like chocolate ice cream. And I get some proportion, 40%. We're going to call that p hat. Or if I ask them a different question, I say, just how tall are you? And then I compute the average height of all the people in this sample. I'll get x bar of height. Then I take another sample of 30 people again. And again I ask them, what percent of you guys like chocolate? Or again I compute their average height. So the distributions we've looked at thus far were the population distributions, where I'm drawing these samples from. The sampling distribution is not the distribution of the people themselves, but the distribution of these statistics computed from these samples. If I took 1,000,000 samples, I'd get 1,000,000 sample proportions, and the sampling distribution, I could then make a histogram of all those 1,000,000 sample proportions, and that would be the sampling distribution. So it's not the distribution of the individuals, it's the distribution of the statistic computed from a sample. Which I know can be a bit of a confusing concept. So if I keep taking samples, I keep getting p hats or x bars, depending on what I'm computing from the sample. I can make a distribution of those. Questions there? So let's say, for argument's sake, let's talk about height. Let's say the average height is 70 inches with a standard deviation of 5 inches. If I pick one person out of the population, I do expect them to be close to the average, that's why it's called the average. But if they fall somewhere out here at the extremes, well, that's not all that unlikely. I could use the empirical rule or the z-table to find the probability that someone is far away from the mean. But what if I take 30 people and compute their average height? Am I more or less assured that that average will be close to the mean compared to had I just taken one person? I'm more assured because if I take one guy, he could fall just about anywhere. If I take 30 and average them, then I'm really a little bit more certain that that average is going to be close to the true population average.
Again, provided they're representative of the...
Provided it's representative, yes, yes. I can't go, poll the UCLA basketball team and get a representative sample of height. But if the sample is representative, I expect it to be really close to that population average. This makes sense intuitively. I'm taking 30 people from the population as opposed to just one. It's the same idea as the more people in my sample, the more accurate results. Maybe think about it from the other way. If I wanted to estimate what is the average height, and I just take one guy and measure him, is that a great estimate?
No.
No, because it could be really far away from what the true mean is. Better that I take 100 guys, measure their height, compute the average, and use that as my estimate of what the average height is in the whole population. So what I'm saying is the sampling distribution will have the same mean as the population distribution, but because I expect the sample statistic to be closer to that mean, it has a shrunken standard deviation. So the sampling distribution has the same mean as the population distribution, but has a smaller standard deviation than the population distribution. And that standard deviation shrinks proportionally to what, do you think? As what increases the sampling distribution standard deviation decreases? The sample size. The larger my sample, the more accurate my results, the more certain I'm going to be that average is near the true mean, whatever that true mean is. So the larger my sample size, the smaller my standard deviation. So what is that sampling distribution? So despite being a somewhat hard concept to think about, the central limit theorem makes it a very simple thing. And here, central limit theorem is not, central doesn't mean like median or mean. Central means of the utmost importance. And this is the most important theorem in all of statistics. It's what makes statistics possible. I'm using p hat here. Again, remember that means sample proportion. I take 100 people, 35 of them like chocolate. P hat is 35%, 0.35. The reason we're using p hats instead of x bars, there is a central limit theorem for x bars. That's chapter 9 in our book. Is that chapter actually gets very confusing. Proportions have an interesting property that if I know p, then I can also just compute the standard deviation. So the mean of my sampling distribution, of the distribution of p hat, is just p itself, where p is the population proportion. So if 40% of all people like chocolate, then p equals 40%. And then p hat being if I took different samples and asked them what proportion of you guys like chocolate, this is that distribution. So it has mean p and a standard deviation that I can compute from p. Imagine if I said IQs have a mean of 100. Can you compute the standard deviation from that? No, that tells you nothing about what the standard deviation is here. Here, if you know p itself, then you know both the mean of this distribution and its standard deviation. Remember Q, you really can't see the board there, but Q just means 1 minus P. It's an abbreviation. I think we had seen that earlier in the class, did we? Maybe not. So I do regret using that abbreviation there, but it's there. So remember Q just equals 1 minus P. If people chose Q as that abbreviation because it looks like a backwards P. So let's do examples of what this actually means. Well, first off, I sure have said a whole lot already in this lecture, but this whole central limit theorem sampling distribution thing boils down to one difference from chapter 6. In chapter 6, my z-score was x minus the mean divided by the standard deviation. And the mean and the standard deviation had to be given. Now I'm going to give you p, and p will be your mean, and then you compute your own standard deviation. So now our z-score is p hat, my sample proportion, minus the mean, which now that we're talking proportions, it's just p, divided by that formula for the standard deviation, square root p times 1 minus p divided by n. So this is the formula for the z-score that we're going to be working with now in chapter 7 and 8. But the good news is, once you compute this, the methods are exactly the same as chapter 6. We'll use the table in the exact same way we did before. So this will be on the board soon if you can't read this out. I mean, it'll be on the slide soon. Yes.
Can you just the difference between p hat and x
Yes.
bar?
The difference between p hat and p is the same as the difference between x and mu. This is just the sample proportion.
And is x bar the sample? What is x bar?
X bar is the sample mean.
Okay.
This is p is the population proportion. So in other words, essentially what we're doing in this chapter is, here's p at the middle of this sampling distribution, meaning any sample I take, I expect to have some value close to p, and then all these p hats from all my different samples fall somewhere around there. And that's what this is telling me. The p hats distribute around their mean, which is p, with this standard deviation here, which we need to know p and n to compute that standard deviation. So the real power of this n of course means it's normally distributed, that's why we can use z-scores, is that even if the population distribution were something very not normal, some weird shape like this, or consider the binomial, which is not a normal distribution, that as long as certain conditions are met, the sampling distribution will be normal. It'll have that bell curve shape, making it very easy to compute probabilities from. So the conditions for this to be true are that the sample must be collected randomly, and the trials, or just individuals in the sample, are all independent of each other. The sample must be large. If n is my sample size and p is the population proportion, then n times p has to be greater than 10. Also, n times 1 minus p has to be greater than 10. And the population needs to be large. The population must be at least 10 times the size of the sample, or another way to say it is the sample must be 1/10 of the population or less. On an exam, I'm not going to ask you to check conditions, because if the conditions fail, then you can't answer the question. The central limit theorem must be true for us to be able to answer the question. So know that these conditions are necessary. It isn't always true, though these are not very strict conditions. They're usually easily met. And on a test, I will not ask you for them. Assume they hold true. So let's get into an actual example of this. Well, first off, I know the question on your mind is, how do I know when to use this stuff, this new z-score? What's the difference between z-scores in Chapter 6 and now in Chapter 7? So I said the population distribution is individuals. Now I'm talking samples, right? So right off the bat, it says 200 randomly selected Americans. It doesn't say, what's the probability one guy got an SAT of 1125 or greater? So that's your hint, that you're talking sampling distribution. Think Chapter 7 methods, because I have 200 people now. So 200 randomly selected drivers were asked if they text while driving. 24% of all American drivers admit to texting while driving. So we check the conditions. N is 200 times P of 0.24. So that says all American drivers. So I know that that's P, not P hat. It's the population proportion. That's greater than 10. 200 times 1 minus P is greater than 10. Again, I won't ask you to check that. This means the distribution is approximately symmetric. Approximately normal, sorry, based on the central limit theorem. So what is the probability that 52 or more of the randomly selected drivers text while driving? So we're strictly going to be talking proportions here. So first we need to convert that 52 or more. If the question is not asked in a proportion, we need to convert it to a proportion. So that's 52 out of 200. The question is asking me the probability that my sample proportion will be greater than 52 out of 200, which is 0.26. So that's what they're asking me. If I take 200 people, what's the probability that 26% or more of them will admit to texting while driving? We're told in the question that P is 0.24. So in any sample I take, I expect about 24% of those drivers to admit to texting while driving. But because samples are random and there's sampling variability, there's some chance that I'm actually going to get 26% or more. Here's the 0.26. What I want is this area here. So you can see this is very similar to what we've been doing once I have the z-score. And that is the only difference that we're encountering. I have a different formula for the z-score. So I apologize for all the erasing on this class. I've never had this little chalkboard space. But so our z-score then is P hat minus P divided by that standard deviation we saw. Which here we have P hat is the 0.26 that they're asking me about. It's a hypothetical value. It's what is the probability this does happen once I take this sample of 200, minus the mean, or the expectation, is what I expect to happen, divided by standard deviation of square root P is 0.24. 1 minus p would be 0.76 divided by n, my sample size of 200. So let's find that z-score. Obviously we have 0.02 in the numerator divided by a standard deviation of. So here's the same thing I just wrote on the board. .030. So in this class, it's generally fine to round everything to 2 decimals. But here for the standard deviations of the sampling distribution, I suggest going to 3 decimals because the first one will usually be a 0. These are typically small numbers. So 0.02 divided by 0.03, that's 0.67. So that's my z-score, 0.67. It has the same exact interpretation it always did. It means that this 0.26 is 0.67 standard deviations away from the mean of 0.24. So now I've rewritten this from the probability that my sample proportion is greater than 26% to the probability that z is greater than 0.67. This is a greater than. So I know this is tough to see. There's a door on the other side, can't even go there. I've rewritten it as the probability that z is greater than 0.67. And at this point, it's exactly like chapter 6. The only thing that changed is how I find my z-score, because now I'm talking about samples. So what do I have to do since it's greater than? Complement 1 minus the probability that z is less than 0.67. So what is that? Go to your z table and find the probability that z is less than positive 0.67. Who has it? So remember, you go to row 0.6, column 0.07, and you should see 0.7486. So our answer is 1 minus 0.7486, which is about 0.25, about 25% chance. So there's a lot of percents around here, so let's put this in a sentence. If 24% of all drivers admit to texting while driving, then there's a 25% chance that in my sample of 200, I'll get 26% of them that text while driving or more. Shall I repeat that? If 24% of all American drivers admit to texting while driving, then there's a 25% chance that out of my 200 drivers, 26% or more of them will admit to texting while driving. This is that sampling variability. I know 24% is the true value in the whole population, but samples are random. So if I take a random sample, there's some chance that my sample, I'll have 26% or more admitting to texting while driving. And the probability of that happening is 25%.
So this formula is the central limit theorem. What would we
Yes.
consider this formula?
Your z-score formula is a product. Our new z-score formula, I erased it, is a product of this. This is the central limit theorem. It tells me the sample proportion is distributed normally with mean p and standard deviation, that formula there. So let's do another example of the same thing. Yes.
Where did that Q equal 1 minus P come in? I don't know if it's.
So the formula, the standard deviation is p, q just means 1 minus p. So it's p times 1 minus p over n. And that's what we have over there. The standard deviation is p is 0.24. 1 minus 0.24 is the 0.76. Divided by n, our sample size, and then square rooted. All right, so similar question. 78% of all lab mice can make it through some maze. If 600 randomly selected mice attempt the maze, what is the probability that more than 80% of them will make it through the maze? So again, 78% is what I expect because I'm told that 78% of all mice can make it through the maze. But certainly there's some chance that I get an exceptional group of mice. And my really clever mice, 80% of them or more can make it through this maze. So what it's asking me is the probability that my sample proportion will be greater than 0.8. The probability that 80% or more of my mice make it through the maze. Again, in the normal distribution, there's no difference between greater than or equal to. The equal to makes no difference. My first step, just like in chapter 6, is to find the z-score. Except that now my z-score has changed. P hat minus p over square root p times 1 minus p over n. So p hat is what they're asking me, 0.8, minus p, which is given in the problem, 0.78, divided by the standard deviation. I'm using p, not p hat, so 0.78 times 1 minus 0.78 is 0.22, divided by n, my sample size, there's 600 mice. So let's compute that z-score. .017 standard deviation for a z-score of 1.18. Once I've reached this point, there's no difference now from the stuff we did in chapter 6. I use the z-table the same way. I've rewritten this as the probability that z is greater than 1.18. It's a greater than, so again I have to use the complement because the table is only written in less than. So I have 1 minus the probability that z is less than 1.18. I go to the table, I look up row 1.1, column 0.08. I get 0.8810. Which is 88%, 100% minus 88%, we get a little less than 12%, approximately 12%. So again, we got a lot of percentages, what do they mean? If in fact 78% of all mice can make it through the maze, then there's a 12% chance that I get this special group of mice, and I get 80% of the mice is making it through the maze, or more. To illustrate it, here's the central limit theorem tells me the sampling distribution is normal. Here's my 0.78 in the middle. I want the probability that I get 80% or more. So this shaded area is the 12% that we arrived at. Questions there? So let's do one more example of these before we take our break. We have that an iPod has 5,000 songs on it. Assume that 15% of the songs in this iPod are classical music. So is that P or P hat, that 15%? It's P. It's telling me the whole population is the 5,000 songs on this iPod, and of them 15% are classical, so that's the population proportion. We randomly pick 100 songs. what is the probability that no more than 10% of the songs will be classical? So I'm being asked the probability that my sample proportion, what does no more than 10% mean? It's 10% or less. So I'm looking for the probability that my sample proportion is less than or equal to 0.1. To illustrate it, I expect 15% of any sample taken from this iPod to be classical music, because that's the true value in the whole population. But there is some chance that I get a set with very little classical music compared to what it should be, 10% or less. And this shaded area is what we're looking for here. So I go to the z-score. P hat minus p would be 0.1 minus 0.15, divided by the standard deviation. 0.15 times 1 minus p is 0.85, divided by my sample size. I have 100 songs in my sample. So let's find this z-score. Negative 0.05 divided by 0.036 gives us a z-score of negative 1.39. So it's telling me that this 10% that I'm computing the probability of is 1.39 standard deviations below the 15% that I expected. So I've rewritten this as the probability that z, always the same relation as our original question, is less than negative 1.39. It's a less than, so do I need to use the complement? No. Anytime it's a less than, the table is already correct. So I'm going to go to row negative 1.3, column 0.09. Looks like 0.0823. And because it was a less than, that's my final answer. Yes.
Oh, there was a P is less or equal to 10%, but now you know that Z is.
Right, so remember, anytime we're talking the normal distribution, or any continuous distribution for that matter, there is no difference between less than or equal to, and greater than or equal to. The reason we don't really talk about in this class, it has to do with calculus. The area under a curve at any specific point is always 0. It has to be a range for it to have a limit. Questions there? So what is this saying? If in fact 15% of all the songs are classical, there's an 8.23% chance that in my sample of 100 songs, I actually get 10% of them being classical or less. So we're talking about variability from one sample to another. Yes?
When you drew the curve and put the 0.15 in the middle, that's not the average, though. Like that wasn't.
It is.
I mean,
if we go back here,
15%.
Because we were told that 15% of all the songs are classical, therefore the average of all samples that we take should be 15%, the true value. And that's what the central limit theorem is saying here. That the mean of all the p hats, the mean of all my sample proportions, is just p. Yes.
You said that it's all 15% also.
Yes. If 15% of all songs are classical, then there's an 8.23% chance that in my 100 songs, I get 10% of them being classical or less. 10% or less being classical. So in other words, we're looking at the probability of getting something other than what we expected. We always expect p, whatever p is. But because of sampling variability, there's a chance we could get something other than what we expect. And that's what we're doing, finding the probability of getting something other